Hello students, today we are going to take some more examples based on descriptions of sets, that is the set builder form and roster form, and then we will take types of sets. Okay, so first example is describe each of the following sets in roster form. So here first is set of all x such that x is a positive integer and divisor of 9. Okay, so we know that 1, that is the divisor of all numbers, then 3 and 9 itself, that is a divisor. So if we write in roster form, it is a 1, 3 and 9. Okay, in roster form we have to write each element separately, and that element is separated by comma. Okay, so this is the roster form of this set. Okay, then second is collection of all sets, collection of all x such that x is less than or equal to mod 2 and x belongs to z. So x less than or equal to mod 2 means it contains 0, 1 and 2. Okay, so when we remove that mod sign, it is a 0, then plus minus 1. Okay, so it is a plus minus 1, then plus minus 2. Okay, because it is less than or equal to mod 2. Okay, so we can write in this way also minus 2, minus 1, 0, 1, 2. Okay, so this is the roster form of this set. Okay, then next one is x, collection of all x such that x is equal to n upon n square plus 1 and n is greater than equal to 1, less than equal to 3, and n belongs to n, that is a natural number. So if we take n is equal to 1, so it is 1 upon 1 square plus 1, so 1 upon 1 plus 1, it is 2. When we take n is 2, so 2 upon 2 square plus 1, 2 square is 4, 4 plus 1 is 5. Then n is equal to 3, 3 upon 3 square is 9, 9 plus 1, 10. Okay, so in this set contain 3 elements, 1 by 2, 2 by 5 and 3 by 10. Okay, understand this, how to write set builder form into roster form. Okay, now we will take next example. The second example is write the set 1 by 2, 2 by 3, 3 by 4, 4 by 5, 5 by 6, 6 by 7, 7 by 8, 8 by 9 and 9 by 10 in set builder form. Okay, so this is in roster form. So how we write in set builder form? If you observe this, numerator is 1, denominator is 2. Numerator is 2, denominator is 3. So everywhere denominator is 1 more than the numerator. Okay, and if we take x is in the form x, collection of all x such that x is equal to n upon n plus 1. Okay, n is starting from 1 and it is up till 9. Okay, so we can write n less than or equal to 9. Okay, n starting from 1, so n belongs to n. So this is the set builder form of this set. Okay, which is written in roster form. Now here we wrote here it is in set builder form. Okay, understand this, how to write in set builder form. Now we will take next example. Third example is write the set 1, 1 by 4, 1 by 9, 1 by 16, 1 by 25 and so on in set builder form. Okay, so if you observe denominator, it is the square of natural numbers. So this set in set builder form we can write collection of all x such that x is equal to 1 upon n square and n belongs to n. Okay, n is started from 1, so n belongs to n, 1 upon n square. Okay, so if you start from 1 upon 1 square 1 upon 2 square 1 by 4, 1 upon 3 square 1 by 9, and so on. Okay, so set builder form of this set is this way. Okay, we can write this way. Now we will take fourth example. The fourth example is write the following sets in roster form. First one is A is equal to a collection of all an, or we can say that set of all an such that n belongs to n, and an plus 1 is equal to 3an, where an is equal to 1 given. Okay, so we can write this set. First, sorry, it is a a1. A1 is 1 given, so it is a 1. Then if we put n is equal to 2, means n is equal to 1, so we will get a2. So a2 is equal to, if we put n is equal to 1 here, then a2 is equal to 3 into a1. So 3 into a1 value is 1, so 3 into 1 is 3. So second term is 3. Then if we put n is equal to 2, so a3. So a3 is equal to 3 into a2. So value of a2 is 3. So 3 into 3, 9. Okay. If we put n is equal to 3, so 3 plus 1, 4. A4 is equal to 3 into a3. So 3 into 9, 27. Okay. And so on. So this is the set in roster form. Then second example is B is equal to set of all an such that n belongs to n. An plus 2 is equal to an plus 1 plus an, and a1 a2 is equal to 1. So here value of a1 and a2 is 1. So first term is 1, second term is 1. Now if we put n is equal to 1, we will get third term, that is a3. So a3 is equal to a2 plus a1. So a2 plus a1 is 1 plus 1, that is a 2. Then if we put n is equal to 2, a4 is equal to a3 plus a2. So a3 plus a2, it is a 3. a5, a4 plus a3, that is a 5, and so on. Okay, so this is the set in roster form. Understand this, how to convert roster into set builder and vice versa. Now we will take next point, that is the types of sets. Okay. So first set is empty set. A set is said to be empty or null or void set. Okay, so this set we can say it is an empty set or null set or void set. So if it has no element and it is denoted by phi or only these two curly brackets. Okay, in this set there is no element, therefore this set is called as an empty set or null set or void set. Okay, and it is denoted by this symbol phi, or we can write in roster form only these two curly brackets. Okay, because here no element is there, so this set is called as an empty set. For example, if we take x such that x belongs to n and x square is or x belongs to r and x square is equal to -2. Okay, so we know that square root of negative numbers we cannot find in real number. So here this set is empty set, or we can say that it is a null set or void set, and it is denoted by phi. Okay, so this is the set of examples which is empty set. Okay, or we can write x such that x is a divisor of, or x is a multiple of 13. X is a multiple of 13 and less than 10. Okay, so there is no any number which is a multiple of 13 and less than 10. So this set is also, we can say that it is an empty set. Okay, understand this? So if in set there is no element, then it is said that empty set, null set or void set, or it is denoted by these two symbols. Okay, phi or these two curly brackets. Okay. Then next type is singleton set. So singleton set means a set consisting of single element is called a singleton set. Okay. For example, we can write x such that x belongs to n and x square is equal to 9. Okay. So we know that square root of x square is equal to 9, then x has two possible values, either plus 3 or minus 3, but here x belongs to n only, that is a natural number, so this set is only contain 3. So this set is called as a singleton set. In set, if contain only one element, then it is called as a singleton set. Okay, understand this? Or for example, we can write this set. Okay, it contains only 5, then this is called as a singleton set. Okay, understand these two sets. Now we will take next point. It is a cardinal number, or cardinal number means number of elements. Okay, how many elements are there in set? It is called as a cardinal number. Okay, so now we will discuss about that. Okay, now we will discuss this terms, that is a cardinal number. First, it is cardinal number. So what is mean by cardinal number? Means here number of elements in the set. How many elements are there in the set? That is called as a cardinal number of that set. Okay, so suppose, okay, in short we can write number of elements in the set is called as cardinal number of set. Is called as a cardinal number of set. So suppose if I am taking example A, set A contain these three elements 1, 2, 3. Then cardinal number of this set is 3. Okay, because this set contains 3 elements and cardinal number is denoted by this n of A. A means this set. Okay, so number of elements in set A is equal to 3. Okay, that is a number. So n of A is equal to 3. Cardinal number means number of elements in the set is called as a cardinal number, and it is denoted by this n of A. Okay, then equivalent sets. If we say that two sets A and B are equivalent, then cardinal number of that two set is equal. Okay, so definition we can write two sets A and B are equivalent if n of A is equal to n of B. Okay, so cardinal number of set A and cardinal number of set B, if it is equal, then that two sets are called as equivalent sets. Okay, so if A contains this 3 element, B contains this 3 elements, so here cardinal number of set A and cardinal number of set B both are equal, because here n of A is equal to 3, n of B is equal to 3. Therefore, these two sets are called as equivalent sets. Okay, understand this? Then finite sets. If set contains finite elements, then it is called as a finite set. Okay, so contain finite elements in a set. Okay, so for example, I am taking A 1, 2, 3, 4, 5. This is is finite set, okay, because we count that element. Okay, so if set contain finite elements in that set, and we can call that set as a finite set, or we can say like this way: if cardinality of the set is finite, then that set is called as a finite set. Similarly, infinite sets, if that set contains infinite elements, then set we call as an infinite set, or we can say that cardinality of set is infinite, then it is called as an infinite set. Okay, so if it contains infinite elements, then that set is called as an infinite set. Okay, we can write example: set of all natural numbers or set of real numbers. Okay, so all these sets are infinite sets. Then next definition is equal sets. Equal sets means if we say that two sets A and B are equal, so two sets A and B are equal if their elements are same. Okay, so if the elements are same, then we can say that two sets are equal. Okay, means suppose A is equal to 1, 2, 3, 4, and suppose B is equal to 2, 3, 1, 4. Okay, so here elements are same, order is different, but elements are same, then we can say that A is equal to B. All the elements of A are in B, or vice versa, all the elements of B are in A. So we can say that these two sets are equal sets. Okay, understand these terms. Cardinal number, that is mean by number of elements in a set. So if we write cardinal number of 5, that is a single empty set, it is a 0. Okay, because no elements are there, so cardinal number of 5 is a 0. So cardinal number means number of elements in set. Equivalent sets means if two sets A and B are equivalent, if the cardinal number is same, that is n of A is equal to n of B. Finite set means contain finite elements. Infinite set contain infinite elements. And equal sets means two sets are equal if their elements are same. Okay, though it is order is different, but elements are same, so therefore we can say that these two sets are equal. Okay, so A is equal to B. Okay, understand this. Now we will take examples based on these concepts. Okay, the first example is which of the following sets are empty sets. Okay, so A is equal to set of all x such that x square minus 3 is equal to 0 and x is a rational given. So if we find roots of this equation, x square is equal to 3, so x is equal to root 3 or minus root 3, plus root 3 or minus root 3. So plus root 3 and minus root 3, they both are irrational numbers. So here x is a rational given, so this set is a empty set. Okay, understand this. Because x square is equal to 3, x is equal to plus minus root 3. So root 3 is a irrational number, but we want x is rational, so this set is empty set. Then b is equal to set of all x such that x is an even prime number. So we know that only 2 is an even prime number, so there is an element, so this is a non-empty set. Okay, this is a singleton set because only one element is there, but it is a non-empty set because at least here one element is there, so we cannot say it is an empty set. Okay, so this is non-empty set. Then here set C is collection of all x such that x greater than 4 less than 5, but here it is given x belongs to n. So when we consider natural number, there is no natural number between 4 and 5, so this set is empty set. Okay, if we say that x belongs to rational number or x belongs to real number, then this is non-empty set. But here x is belongs to n, so between 4 and 5 there is no any natural number, so this set is empty set. Then this one, set D is set of all x such that x square is equal to 25 and x is an odd integer. So we will get, if we solve this equation, x is equal to plus minus 5, both are odd integers. So in this set contain minus 5 and plus 5. So this is non-empty set. Okay. So only two sets are empty sets. Okay. This C and A. So A and C are empty set, other two are non-empty set. Okay. Understand this? Now we will take second example. Second example is find the pairs of equal sets from the following sets, if any, give reason. Okay. So A is equal to 0 means set contain 0. Okay. So this is singleton set. Okay, because 0 is the element of this set, so this is singleton set. Now we have to find other sets. B is given set of all x such that x greater than 15 and x less than 5. Okay, so at a time x greater than 15 also and x less than 5 also, so this is not possible, so this set is 5 or empty set. Then C, set of all x such that x minus 5 is equal to 0 means only 5 is there. Then D, set of all x such that x square is equal to 25, so this set contains minus 5 and 5. Okay, because here set is not, means x is not defined in which set it is, means natural number or integers. Okay, it is not given, so we have to consider both values, minus 5 and 5. Okay, then set E is given set of all x such that x is an integral positive root of x square minus 2x minus 15 is equal to 0. So if we find roots of this, then that roots are plus 5 and minus 3. So we have to take only positive root. So here only 5 is there. Okay. So if we observe this, C and E, these two sets are equal sets because in these two sets elements are same. Okay. Here element is 5 in set E, that is also 5. So only C and E, these two sets are equal sets. Okay, understand this? And if they ask which are equivalent sets, so here A, C and E, these are equivalent sets because cardinal number of this set is 1 for each set. So here also one element, here also one element, and in E also one element is there. So these three are equivalent sets. Okay, but equal sets are only C and E. Okay, understand this? Now we will take third example. Example 3 is which of the following sets are finite and infinite. Okay, so first one is A is equal to set of all x belongs to z, and x square minus 5x plus 6 is equal to 0. So if we find roots of this this quadratic equation, then it is a 2 and 3. Okay, so this set contains finite elements, so this is finite set. Okay, so we can write here A is a finite set. Then B is equal to here set of all x belongs to z and x square is even. So we have to collect all x whose x square is even. So all these numbers are there, even numbers, minus 6, minus 4, minus 2, 0, 2, 4, 6 and so on. Okay, so all even numbers whose square is even. So we can write this is an infinite set. Okay. So B is an infinite set. Then C is the collection of all x belongs to z and x square is equal to 36. So we know that if x square is equal to 36, x is equal to minus 6 and plus 6. Okay, or minus 6, 6. So this is a finite set, only two elements are there. So C is a finite set. Okay. Then D is the set of all x such that x belongs to z and x greater than minus 10. So in this set contain minus 9, minus 8, minus 7, minus 6 and so on. Okay. So in this set elements are infinite. So this set is infinite set. Okay, so A and C, these are finite set, and B and D are infinite set. Okay, understand these terms. Now for more practice, solve example in given worksheet.